Welcome to Ultimate Sleep Doctor. Tonight, we'll gently explore a realm beyond our everyday perception. Let's turn our attention to quantum physics, a world where reality itself seems to shimmer and shift, built not of solid matter, but of probability and energy. It's a place where particles exist in multiple states at once, and observation fundamentally alters what we see. There's a quiet beauty in this uncertainty, a deep connection between the smallest scales and the vastness of existence. Perhaps contemplating these mysteries can help release the day's held tension. If you find these explorations soothing, please consider liking this video and subscribing to Dr. Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like clouds across a twilight sky. Let's begin. The world, as we often experience it, seems built of smooth, continuous things. A ball rolling across grass, a stream flowing down a mountain, the sound of a musical instrument. All these things appear to be made of a steady, unbroken flow of energy. But at the very, very small scale of the universe, things behave in a truly astonishing way. They don't always follow the rules we're used to. And one of the first, and perhaps most beautiful, demonstrations of this strange behavior came from an experiment involving light and metal. In 1880, a young German physicist named Heinrich Hertz was studying electromagnetic waves, those ripples in space that carry radio signals. He sent a beam of radio waves through a tube filled with hydrogen gas. This tube was cleverly designed so that the radio waves would strike the gas, causing it to glow. Hertz then noticed something peculiar. When he shone a light, like sunlight, onto the glowing gas, it would also start to glow more intensely. It was as if the light was somehow pushing the gas to emit more light. This observation sparked a series of investigations, and it was around this time that George Frederick Thomson, later known as George Goddard, conducted a remarkably important experiment. Goddard set up a similar apparatus, but instead of using hydrogen gas, he used a metal plate, typically zinc, placed inside a closed tube. He shone a beam of light, ranging from ultraviolet to red, onto the metal plate. Now here's where it gets really interesting. Goddard observed something nobody had ever seen before. When he shone light of a certain frequency, a specific color, onto the zinc plate, the plate would suddenly emit tiny particles of electricity called electrons. These electrons would zing away from the metal surface, creating a small electrical current. The surprising part wasn't that light could cause electrons to leave the metal. It was how much electrons were emitted and how quickly it happened. He meticulously varied the color of the light he used, the frequency, and he discovered a crucial relationship. He found that only light of a certain frequency or a certain color could cause the plate to release electrons at all. And more importantly, the brightness of the light, its intensity, directly affected the number of electrons that were emitted. Brighter light meant more electrons, and dimmer light meant fewer. Furthermore, the energy of the light also played a critical role. The shorter the wavelength of the light, the more energetic its photons were, and the more electrons they could knock free. It seemed utterly baffling. Classical physics, which described the world as smooth and continuous, couldn't explain what was happening. It was as if light, which we thought of as a wave, was also behaving like a stream of tiny bullets. This contradiction led to a revolutionary idea proposed by Albert Einstein in 1905 that would eventually reshape our understanding of light and matter. Einstein's explanation, based on Max Planck's earlier work about energy quantization, suggested that light wasn't just a wave. It was also made up of discrete packets of energy. He called these packets quanta, a word that would soon become central to the field of quantum physics. Each quantum of light has a specific amount of energy, determined by its frequency. Higher frequency light, like blue or violet, has more energetic photons, while lower frequency light, like red, has less energetic photons. Think of it like this. Imagine you're throwing tennis balls. If you throw them gently, they'll travel a short distance before stopping. But if you throw them with a lot of force, they'll travel much further. Light, according to Einstein, behaves similarly. Instead of a continuous flow of energy, it's delivered in these tiny, individual tennis balls of energy, the photons. When a photon strikes the metal plate, it's like a single, energetic tennis ball hitting the surface. If the photon's energy is sufficient, if it has enough energy, it will transfer that energy to an electron in the metal. This transfer is enough to overcome the electron's binding force to the metal, allowing it to break free and fly away as an electrical current. The intensity of the light determines how many photons are hitting the metal plate at once, and therefore, how many electrons are freed. The frequency of the light dictates the energy of each individual photon. The energy of a photon is directly related to its wavelength by the equation E equals hf, where E represents the energy, h is a constant, Planck's constant, and f represents the frequency. This equation beautifully links the wave-like properties of light frequency to its particle-like properties energy. This concept of light behaving as both a wave and a particle is a cornerstone of quantum mechanics. It wasn't immediately accepted. It was a radical departure from classical physics. However, the photoelectric effect, the observation that light can eject electrons from a metal surface, provided incredibly strong evidence for Einstein's theory and paved the way for a truly revolutionary understanding of the universe. It's a reminder that the smallest things in the world operate in ways that are profoundly different from our everyday experience, and that sometimes the most surprising discoveries come from observing the strangest phenomena. The world of quantum physics is full of these surprises, waiting to be uncovered. The world of quantum physics often feels like a dream, doesn't it? Like something built from impossible shapes and shimmering, shifting probabilities. And at its heart lies a particularly strange and beautiful concept, wave-particle duality. It's the idea that things we normally think of as solid, like electrons, can behave as waves, and that waves, like light, can sometimes act like tiny particles. It's not that electrons are sometimes waves and sometimes particles. It's more that they exhibit characteristics of both, depending on how we observe them. Consider an electron, one of the fundamental building blocks of matter. We generally picture it as a tiny, indivisible sphere, a little bullet zipping around the nucleus of an atom. But experiments, starting in the early 20th century, began to challenge this simple image. One of the most groundbreaking was the double-slit experiment, and it's a story that continues to fascinate scientists. In this experiment, physicists fired a beam of electrons towards a barrier with two narrow slits. You might expect, if electrons were simply particles, that they would pass through one slit or the other and create two distinct bands on a screen behind the barrier. That's what would happen if you shot bullets through two holes in a wall. Two piles of bullet impacts would form. However, what actually happened was astonishing. Instead of two bands, an interference pattern emerged on the screen. This pattern, composed of alternating bright and dark bands, is exactly what you'd expect to see when waves interfere with each other. Waves, remember, can spread out and overlap, creating regions of higher and lower intensity. When two waves combine constructively, their amplitudes add together, resulting in a stronger wave. When they combine destructively, they cancel each other out, creating a weaker wave. The electrons, behaving like waves, were passing through both slits simultaneously and interfering with themselves. It's as if the electron went through both slits at the same time, creating the interference pattern. Now you might be thinking, but if the electron went through both slits, how did it arrive as a single, localized particle on the screen? That's the core of the mystery. It's not that the electron somehow split into two copies and then recombined. The electron, at its fundamental level, doesn't have a definite position until it's measured. Before measurement, it exists in a superposition of states, meaning it's potentially in multiple places at once, described by a wave function. The wave function describes the probability of finding the electron at a particular location. The wave itself isn't a physical thing. It's just a mathematical representation of the electron's possible states. When the electron interacts with something like the screen, it collapses the wave function. The act of measurement forces the electron to choose a specific location, and we observe it as a single particle. It's like the wave function is a blurry, probabilistic cloud, and when you try to focus it, by observing its position, it suddenly becomes sharp and definite. It's important to understand that this isn't about electrons being tricked or misbehaving. It's a fundamental property of the universe at its smallest scales. Quantum mechanics tells us that reality isn't always neatly defined and predictable like the world we experience every day. Instead, it's inherently probabilistic, based on probabilities and potential outcomes. Consider the electron's momentum. Before we measure it, its momentum isn't a fixed value. It's described by the wave function. The wave function tells us the probability of finding the electron with a particular momentum. When we measure the electron's momentum, the wave function collapses, and we obtain a definite value for the momentum. The wavelength associated with an electron's momentum is inversely proportional to its momentum. This relationship is described by the de Broglie equation. Wavelength lambda equals hp, where h is Planck's constant, a tiny fundamental constant, and p is the electron's momentum. This equation beautifully links the wave-like behavior of particles to their momentum. The double-slit experiment and the wave-particle duality has been rigorously tested countless times with various types of particles, photons, neutrons, even larger molecules particles consistently exhibiting these strange behaviors. It's not just electrons that play this game. It's a universal phenomenon at the quantum level. It's tempting to try and find a way to explain wave-particle duality with everyday intuition. But the quantum world simply doesn't operate according to our classical understanding. It's a world of fuzziness, probabilities, and interconnectedness. It challenges our assumptions about the nature of reality itself. The concept of wave-particle duality isn't just a theoretical curiosity. It has practical implications. For example, technologies like electron microscopes rely on the wave-like properties of electrons to achieve resolutions far beyond what's possible with light. Ultimately, wave-particle duality is a profound reminder that the universe is far stranger and more beautiful than we often imagine. It's a testament to the power of scientific inquiry and the ongoing quest to understand the fundamental laws governing our reality. It's a story of particles that can be waves, of probabilities and potential, and of a universe that continues to surprise and challenge our perceptions. And perhaps, just perhaps, it encourages us to embrace the unknown and appreciate the inherent mystery at the heart of existence. The universe, at its most fundamental level, doesn't like to be pinned down with simple answers. It's a place of delightful fuzziness, of probabilities and whispers rather than hard, defined facts. For a long time, physicists had a comfortable picture. They could, in principle, know exactly where a particle was and how fast it was moving at the same time. They used mathematics, beautiful, precise equations, to describe this knowledge with incredible accuracy. Then, in the 1920s, Werner Heisenberg unveiled a startling discovery, a fundamental limit to what we can truly know about the smallest building blocks of reality. This limit isn't a mistake in our measuring instruments. It's woven into the very fabric of the universe itself. It's called the uncertainty principle, and specifically, it deals with the relationship between a particle's position and its momentum. To understand the uncertainty principle, let's consider what it means to know the position of an electron. We might set up an experiment. We shine a beam of light, photons, at the electron and try to detect where it bounces off. The light, acting as a probe, interacts with the electron, revealing its location. But here's the rub. As the light interacts with the electron, it inevitably disturbs it. That beam of light, even though incredibly small, carries energy. When a photon hits an electron, it transfers some of that energy, changing the electron's momentum, essentially its speed and direction. The more precisely we try to determine the electron's position, the more we disturb its momentum, and vice versa. It's like trying to find a small, slippery fish in a dark aquarium. If you shine a bright light directly on it, the fish will dart away, startled by the brightness, and you'll have no idea where it was before. But if you try to observe it in the dark, using a very faint light, you'll be able to track its movement, but you'll be completely unsure of exactly where it is at any given moment. There's no way to perfectly know both simultaneously. The act of observing fundamentally alters what is being observed. This isn't about limitations of our instruments. It's a consequence of wave-particle duality. Electrons, like light, exhibit wave properties. When we try to pinpoint an electron's location, To make it behave more like a particle, we are forcing it to choose a definite position, which inevitably involves a certain spread of momentum. Conversely, if we want to know the electron's momentum precisely, we must allow it to spread out over a wider range of positions, becoming a wave. The more we know about its momentum, the less we know about where it is, and vice versa. The uncertainty principle isn't just a problem for electrons. It applies to all quantum particles, photons, quarks, and even larger particles like protons and neutrons. The principle is expressed mathematically as a fundamental inequality, deltax greater or equal to h/2, where deltax represents the uncertainty in position, delta represents the uncertainty in momentum, and h stroke, pronounced h bar, is a very small constant that relates to Planck's constant. This equation essentially states that the product of the uncertainties in position and momentum must be greater than or equal to a minimum value. It's a concise declaration of the unavoidable fuzziness. Let's consider a simple example. Suppose we are trying to measure the momentum of a single photon. To do this accurately, we need to interact with it, for example, by reflecting it off a mirror. But even a tiny interaction will change the photon's direction and speed, introducing uncertainty into its momentum. The more precisely we determine the photon's direction, the more we disturb its momentum. Conversely, if we want to know the momentum precisely, we must allow the photon to travel a longer distance, making its position more uncertain. It's important to understand that the uncertainty principle doesn't mean that we can't ever know the position or momentum of a particle. It simply means that there's a fundamental limit to how precisely we can know them simultaneously. We can always make our measurements more accurate, but we can never eliminate the inherent uncertainty. It's not about limitations of our technology. It's a consequence of the universe's structure. Furthermore, the uncertainty isn't random. The values of deltax and delta aren't simply arbitrary fluctuations. They are correlated. When we know the position of a particle with greater certainty, we know its momentum with less certainty, and vice versa. The uncertainty isn't a chaotic, unpredictable element. It's a fundamental connection between position and momentum. The uncertainty principle has profound implications for our understanding of the universe. It challenges our classical intuition that we can always know everything about a system if we just observe it carefully enough. It's a cornerstone of quantum mechanics, providing the basis for understanding phenomena like quantum tunneling, where a particle can pass through a barrier even though it doesn't have enough energy to overcome it, and the probabilistic nature of quantum events. It suggests that reality at its deepest level isn't deterministic, but rather described by probabilities. It's a strange and beautiful concept, this inherent fuzziness of the universe. It reminds us that our knowledge of the world is always incomplete, always subject to the limitations imposed by the very nature of reality. It encourages us to embrace the mystery, to appreciate the elegance of a universe where things aren't always neatly defined, but rather exist in a state of delightful quantum uncertainty. And perhaps most remarkably, it suggests that the universe isn't something we passively observe, but rather that our act of observation actively shapes what we perceive. The universe, at its most fundamental level, doesn't always play by the rules we're used to. Everyday experience tells us that if you throw a ball at a wall, it bounces back. It hits the wall, loses some energy, and continues on its way. But in the quantum realm, things get stranger. It's a realm where probabilities rule and where particles, like tiny electrons, can seemingly defy the very notion of barriers. This is the phenomenon of quantum tunneling. Consider an electron, a fundamental particle of matter. We understand it as a wave, a rippling disturbance that expands outward from its point of origin. This wave doesn't abruptly end. Instead, it continues, spreading into the space around it. The extent of this wave is described by its probability distribution. It indicates where there's a higher chance of finding the electron. Now, imagine this electron approaching a barrier, something solid like a wall made of atoms. Classically, if the electron doesn't have enough energy to overcome the barrier's height, it simply stops at the barrier's edge and doesn't go through. It's a definite stop. However, quantum mechanics tells us a different story. Because the electron exists as a wave, that wave doesn't just vanish when it encounters the barrier. Instead, a portion of the wave penetrates through the barrier, even if the electron doesn't have enough energy to clear the barrier's height. It's as if the barrier isn't quite a solid wall, but more like a fuzzy veil. The wave doesn't break apart. It diminishes in intensity as it passes through, but a small part of it still emerges on the other side. The probability of this happening is related to the width and height of the barrier. A wider and taller barrier means a lower probability of tunneling. The barrier isn't a complete obstruction. It's a region of reduced probability. The electron doesn't travel through the barrier in the way we understand travel. There's no physical movement across the barrier. It's the wave function, the mathematical description of the electron's probability distribution, that finds a path through the barrier. Think of it like this. If you drop a pebble into a calm pond, the ripples spread outwards. If the pond had a small, perfectly smooth depression, some of the ripples would inevitably curve around the depression and continue on the other side. The electron is doing something similar, but instead of ripples in water, it's the wave function that's bending and passing through the barrier. The deeper we delve into this, the more abstract it becomes. The wave function doesn't represent a specific electron at a specific location. Instead, it describes the possibility of finding the electron on the other side. It's a mathematical representation of the probability of the electron appearing there. The tunneling probability isn't a fixed number. It changes depending on the energy of the electron, the material of the barrier, and the shape of the barrier itself. Now, let's consider an example. In a device called a tunnel diode, engineers intentionally create very thin barriers to allow electrons to tunnel through. By controlling the width and the material of the barrier, they can precisely control the flow of electrons, creating a device that operates in a fundamentally quantum way. This is a direct consequence of quantum tunneling. The implications of quantum tunneling extend far beyond simple device design. It plays a crucial role in nuclear fusion within the sun. The nuclei of atoms are held together by the strong nuclear force, but they are also repelled by each other's positive charges. Quantum tunneling allows the nuclei to get close enough to overcome this repulsion and fuse together, releasing tremendous amounts of energy. Without quantum tunneling, the sun wouldn't shine. Furthermore, quantum tunneling is essential in certain types of radioactive decay. When a nucleus decays, it emits a particle, such as an alpha particle. The particle doesn't simply blast itself out of the nucleus. Instead, it tunnels through the potential barrier created by the strong nuclear force, allowing it to escape. It's important to remember that quantum tunneling is a probabilistic phenomenon. We can't predict with certainty whether an electron will tunnel through a barrier at a given moment. We can only calculate the probability of it happening. This inherent uncertainty is a hallmark of the quantum world. Scientists continue to explore and utilize quantum tunneling in new technologies, including advanced sensors and potentially even new forms of computing. The more we learn about this extraordinary phenomenon, the more we realize how profoundly the universe operates at its most fundamental level, a level where classical intuition simply doesn't apply. It's a reminder that the universe is full of surprises, waiting to be uncovered through the patient exploration of the quantum realm. The universe, at its most fundamental level, doesn't behave like the smooth, predictable world we experience every day. Instead, it operates according to rules that are profoundly counterintuitive, where things can exist in multiple states simultaneously, and where observation itself fundamentally alters what we see. This peculiar realm is described by quantum mechanics, and the heart of this theory is a single, incredibly powerful equation, the Schrödinger equation. It's not an equation that tells us how something will move, but rather an equation that describes how the probability of something moving changes over time. Think of it like a recipe for a wave. It dictates how that wave evolves, grows, or shrinks. The Schrödinger equation itself is a rather elegant mathematical expression, looking something like this. I delta psi slash delta t equals h stroke 2 slash 2 m2 psi. Don't worry too much about the symbols for a moment. I is the square root of -1, a crucial component in describing wave behavior. H stroke, pronounced h bar, is the reduced Planck constant, a tiny number that governs the scale of quantum effects. Psi is the wave function, and it's the key to everything. The wave function isn't a physical wave like a ripple in water. Instead, it's a mathematical function that describes the probability of finding a particle at a specific location and time. The square of the wave function's magnitude gives you this probability density. Delta psi slash delta t represents the rate of change of the wave function with respect to time. 2 is the Laplacian operator, a mathematical tool that describes the curvature of the wave function, essentially, how quickly the wave is changing shape. Finally, m is the mass of the particle. Let's consider a simple system. A single, tiny particle, like an electron, confined within a one-dimensional box. Imagine a box of length L. This is a fantastic starting point because it provides a tractable problem with a clear, well-defined solution. The Schrödinger equation for this electron in a box takes a particularly beautiful form. When you plug the appropriate boundary conditions, that the wave function must be 0 at the edges of the box, meaning the electron can't exist outside the box. Into the equation, you arrive at a specific set of solutions. The solutions for the electron in a box aren't single, smooth waves. Instead, they are a series of standing waves, much like the standing waves you might see on a guitar string. These standing waves are characterized by specific wavelengths that are multiples of half the box length. Lambda equals 2 nln, where n is an integer. Each of these wavelengths corresponds to a particular energy level that the electron can occupy within the box. The energy levels aren't continuous, they're quantized. This means the electron can only exist at specific, discrete energy values. It's like a staircase. You can only stand on the steps, not in between them. These energy levels are determined by the equation E equals hf equals h stroke 2k 2/2m, where E is the energy, h is Planck's constant, f is the frequency, k is the wave number related to wavelength, and m is the mass. The lowest energy level, corresponding to the ground state, is particularly important. The electron will naturally tend to occupy this state because it's the most stable configuration. Now let's consider a slightly more complex system, a particle in 3 dimensions, again trapped within a box. The Schrödinger equation becomes a bit more involved, and the solutions are 3-dimensional standing waves. These waves have characteristic patterns, nodes, points of zero amplitude along each axis that reflect the confinement of the particle. The number of nodes in each direction determines the energy levels, and like in the one-dimensional case, the energy levels are quantized. The solutions for a particle in 3 dimensions are often visualized using electron density maps, which show the probability of finding the particle at different points within the box. Beyond simple boxes, the Schrödinger equation can be adapted to describe more complicated potentials, forces that act on the particle. The solutions become more intricate, but the fundamental principle remains the same. The energy levels of the system are quantized. Scientists have used the Schrödinger equation to accurately predict the behavior of electrons in atoms and molecules, explaining a vast range of chemical and physical phenomena. Solving the Schrödinger equation, even for these simple systems, isn't always straightforward. Often, the equation needs to be solved numerically, using computers to approximate the solutions. However, the elegance and predictive power of the equation are undeniable. It's a cornerstone of modern physics, a testament to the fact that the universe, at its most fundamental level, operates according to rules that are both strange and profoundly beautiful. The wave function and the probabilities it embodies ultimately determine the behavior of everything around us, from the smallest subatomic particles to the largest stars. It's a journey into the heart of reality itself. The universe, at its most fundamental level, doesn't quite play by the rules we're used to. It's a place where things aren't neatly defined, where possibilities exist simultaneously before being observed. Let's consider a tiny particle, something like an electron. We might naturally assume that an electron is somewhere, occupying a specific location in space at any given moment. But quantum mechanics tells us that's not quite how it works. Instead, an electron, prior to measurement, exists in a state of what's called superposition. Superposition isn't about the electron being in two places at once in the way we typically understand. It's more accurate to say that it exists as a blend, a probability wave of all the possible locations it could be. Think of it like this. You're holding a coin before you flip it. Before it lands, it's neither heads nor tails. It's in a state of being both possibilities simultaneously. The electron, similarly, isn't definitively in one position. It's described by a mathematical function, the wave function, that dictates the probability of finding it at any given point. This wave function isn't a physical wave like a water wave. It's a mathematical description of the electron's state, representing the range of potential locations and the likelihood of observing it in each of those places. The higher the amplitude of the wave at a particular point, the greater the probability of finding the electron there. The wave function isn't something we can see, but it's the most accurate way to represent the electron's existence until we actively try to determine its location. Let's delve a little deeper into this mathematical description. The wave function is often depicted as a graph, a sinusoidal wave. The horizontal axis represents position, and the vertical axis represents the amount of the electron's probability at that position. A smooth, regular wave indicates a uniform probability distribution, meaning the electron has an equal chance of being found anywhere along that line. However, the wave function can be more complex, shaped by factors like the forces acting on the electron, such as electromagnetic fields. These forces cause the wave to distort, changing the probabilities. Now consider a simple experiment, a double-slit experiment. In this experiment, electrons are fired at a barrier with two slits. Classically, we'd expect the electrons to pass through one slit or the other, creating two distinct bands on a screen behind the barrier. However, what actually happens is far stranger. The electrons create an interference pattern, a series of bright and dark bands, just like waves would. This suggests that each electron is somehow passing through both slits simultaneously. The explanation lies within superposition. Before being observed, each electron exists in a superposition of states, meaning it's effectively traveling through both slits at once. This isn't a matter of the electron splitting into two copies. It's a fundamentally different way of describing its behavior. The wave functions from each slit overlap and interfere with each other, creating the interference pattern we observe on the screen. The act of observation fundamentally changes the system. When we try to determine which slit the electron passes through, for example, by placing a detector near one of the slits, the superposition collapses. The electron chooses one specific location, and the interference pattern disappears. The measurement forces the electron to commit to a single state. It's as if the electron was aware of our presence and consciously decided to reveal its location. It's vital to understand that the electron isn't simply moving faster and somehow managing to pass through both slits. The wave function describes the potential for the electron to be in multiple places at once. It's not a physical phenomenon in the way we typically think about it. The mathematics are providing us with the most accurate description of its possible behaviors. The concept of superposition is one of the most baffling aspects of quantum mechanics, and it's been the subject of debate and interpretation for decades. It challenges our intuitive understanding of reality, suggesting that the universe is fundamentally probabilistic, and that observation plays a crucial role in shaping what we perceive. Even now, scientists continue to explore the implications of superposition, seeking to unlock its secrets and harness its potential for technologies like quantum computing. The implications extend far beyond simple experiments. Superposition is a core principle in understanding the behavior of atoms and molecules, and it's the basis for many quantum phenomena, including entanglement, another fascinating concept where two particles can be linked together in such a way that they share the same fate, no matter how far apart they are. The superposition of states allows for a universe of possibilities, a realm where uncertainty reigns supreme, and where the act of looking changes everything. And as we venture deeper into the quantum world, we discover that reality itself might be far stranger and more wonderful than we ever imagined. The universe, as we've come to understand it, isn't always neatly defined. It's a place where certainty seems to relinquish its grip, particularly when we delve into the realm of quantum mechanics. It's a realm where things can be in multiple states simultaneously, where particles can seemingly pass through barriers, and where the very act of observing something can fundamentally change it. Today, we're going to explore one of the most astonishing and perplexing aspects of this world: quantum entanglement. Entanglement describes a connection between two or more particles that is far deeper than anything we experience in our everyday lives. It's a connection that appears to defy the limitations of distance and time. Let's consider two photons, for example, particles of light, that have been created together in a very specific way. Perhaps they've interacted in a way that forces them to have opposite polarizations, meaning one is spinning vertically and the other horizontally. Initially, each photon is in an undefined state. It doesn't have a definite polarization until we measure it. But the instant we measure the polarization of one photon and find it to be vertical, we instantaneously know that the other photon must be horizontally polarized, no matter how far apart they are. This isn't simply a matter of the photons being pre-programmed with opposite polarizations from the beginning. Before measurement, both photons exist in a blurry superposition of both states. They're neither vertically nor horizontally polarized. They're in a combined state of both possibilities. It's the act of observing one that forces both into a definite state. This seems bizarre because it suggests a correlation far stronger than anything allowed by classical physics. Think about throwing two coins across a room. If you flip them, you might get heads and tails, but you don't know what the other coin will land on until you look at it. The outcome of one coin doesn't instantly affect the other. With entangled particles, however, the connection is immediate and independent of distance. Einstein famously called this spooky action at a distance because it appeared to violate his theory of relativity, which states that nothing can travel faster than the speed of light. The crucial point is that before measurement, neither photon possesses a definite polarization. The measurement of one doesn't cause the other to take on a specific value. Rather, the act of measurement reveals a shared, pre-existing correlation. It's like a secret language that the universe seems to be using. This isn't about sending signals. It's about a fundamental interconnectedness. Imagine two dancers performing a routine. They are perfectly synchronized, but neither one dictates the movements of the other. They are connected through the choreography, and when one makes a movement, the other responds instantly, but neither movement caused the other to move. Scientists have conducted countless experiments to test the reality of entanglement. One famous experiment, devised by Elaine Aspect and his team in the 1980s, involved using entangled photons to determine whether they were communicating faster than light. The results consistently showed a correlation that was far too strong to be explained by any local, classical theory. The photons behaved as though they were linked in a way that transcends space and time. However, it's essential to understand that entanglement doesn't allow for faster-than-light communication in the traditional sense. While the correlation is instantaneous, you can't use it to send a message. The outcome of measuring one photon is random. You can't control whether it will be vertically or horizontally polarized, and therefore you can't encode a specific message into that outcome. The correlation only becomes apparent when you compare the results of measurements made on both particles. The implications of entanglement are still being explored, and it's a cornerstone of developing technologies like quantum computing and quantum cryptography. Quantum computers leverage entanglement to perform calculations in ways that are impossible for classical computers. Quantum cryptography uses entanglement to create unbreakable codes, because any attempt to intercept the communication would inevitably disturb the entangled state, alerting the sender and receiver. Furthermore, entanglement challenges our fundamental understanding of reality. It suggests that the universe isn't made up of separate, independent objects, but rather of interconnected systems. The concept of locality, the idea that an object is only directly influenced by its immediate surroundings, is challenged at the quantum level. It's a humbling realization, isn't it? The universe holds secrets that we are only beginning to grasp. Quantum entanglement represents one of those profound mysteries, a reminder that the most fundamental laws of nature are often the most bewildering. The connection between these entangled particles hints at a deeper, more unified reality than we could have previously imagined. It's a subtle, shimmering thread woven through the fabric of existence, a reminder that the universe is far stranger and far more beautiful than we might have thought. The universe, at its most fundamental level, isn't quite as neat and tidy as a spinning top. While rotations are familiar to us, the Earth orbiting the Sun, a skater spinning on ice, a child whirling a toy, the reality of subatomic particles reveals a far stranger property: intrinsic angular momentum, often simply called spin. It's a characteristic woven into the very fabric of their existence, a form of momentum that isn't tied to their movement through space. Instead, it's an inherent, internal property, much like a tiny, hidden gyroscope residing within each particle. This spin isn't derived from an object physically rotating in the way we typically understand. It's an intrinsic quantum mechanical effect. To picture it, let's consider an electron. Electrons are tiny, negatively charged particles that orbit the nucleus of an atom. but instead of circling the nucleus in a predictable, classical orbit, an idea that didn't quite work out with the early formulations of quantum mechanics. The electron behaves as if it's constantly spinning, even though it doesn't have a defined path. This spinning doesn't correspond to a measurable orbital rotation. It's a property that exists regardless of the electron's motion. The mathematics behind this is elegant and sometimes perplexing. Quantum mechanics describes particles not as point-like objects, but as wave functions. These wave functions are mathematical descriptions of a particle's possible states. When we apply the equations that govern these wave functions, we find that the particle's momentum isn't just related to its velocity. It's also linked to this spin. The result is a vector quantity, meaning it has both magnitude and direction. Now here's where it gets particularly fascinating. Spin isn't always a continuous quantity. It exists in discrete quantized units. For electrons, the most common spin value is spin 1,2. This means the spin angular momentum is exactly 1 unit of Planck's constant, h/2 pi, divided by 2. Think of it like stairs rather than a ramp. You can only stand on specific steps, not anywhere in between. The magnitude of the spin is always the same, but its direction can be oriented in different ways. This is described by what we call spin quantum numbers. These quantum numbers, in the case of a single spin 1,2 particle, are represented by the values +1,2 and -1,2. These states are often referred to as spin up and spin down. These aren't literal up and down directions, but rather specific orientations of the spin vector in space. It's important to understand that a particle doesn't choose to be spin up or spin down. It simply exists in one of these states. The act of measurement forces the particle to choose a particular state. The implications of spin are profound. Consider atoms. Electrons occupying different energy levels within an atom aren't simply occupying different distances from the nucleus. They are also existing in different spin states. These spin states interact with external magnetic fields. This interaction is the basis for technologies like magnetic resonance imaging, MRI. When a magnetic field is applied, the electron's spin creates a tiny magnetic field, and the absorption and emission of radio frequency energy allows doctors to create detailed images of the inside of the body. It's not just electrons that possess spin. All fundamental particles, quarks, leptons, bosons, are associated with intrinsic angular momentum. Photons, for example, have a spin of 1. The spin of a particle influences its behavior in magnetic fields and also plays a key role in the fundamental forces of nature. The conservation of angular momentum is a cornerstone of quantum mechanics. It dictates that the total angular momentum of a system must remain constant unless acted upon by an external torque. Now, let's talk about spin statistics. Just as photons come in pairs, 2 photons with the same energy but opposite spin, many other particle interactions also involve the exchange of angular momentum. These interactions are mediated by force-carrying particles, such as the gluon in the strong nuclear force. Furthermore, spin isn't just an abstract concept. It's a measurable quantity. Scientists use sophisticated instruments like mass spectrometers and electron spin resonance spectrometers to directly detect and measure the spin of particles. These measurements provide crucial evidence for the validity of quantum mechanics. It's a truly bizarre aspect of reality. The fact that particles possess this intrinsic angular momentum without any apparent external cause challenges our everyday intuitions about how the world operates. It suggests a universe far more complex and counterintuitive than our macroscopic experience would lead us to believe. The concept of spin has fueled decades of research, leading to a deeper understanding of the fundamental forces governing the universe and paving the way for groundbreaking technologies. It is a reminder that at the smallest scales, the laws of physics are often remarkably different from what we observe in our daily lives. The universe, at its core, is filled with tiny, spinning particles, each contributing to the intricate dance of existence. The universe, as we've begun to understand it, isn't quite like a box full of tiny, solid billiard balls. It's far stranger, far more fluid. For a long time, physicists wrestled with the idea of particles, little chunks of matter, as the fundamental building blocks. But the more deeply they probed the nature of reality, the more they realized this picture was incomplete, a beautiful but ultimately inaccurate approximation. The true story of the universe, it turns out, involves something far more pervasive and fundamental: fields. Consider a calm, still lake. It appears smooth and undisturbed, right? But beneath the surface, there's a constant, invisible activity. The water molecules are constantly vibrating, moving, interacting with each other. These vibrations are always present, even when the lake seems perfectly still. We can't see them directly, but they are undeniably there. Quantum field theory, QFT, takes this idea and applies it to the entire universe. Instead of thinking of particles as the basic ingredients, QFT proposes that the universe is filled with fundamental fields. These aren't like the fields we experience in our everyday lives, magnetism or gravity. These are completely abstract, underlying structures that permeate all of space and time. For every type of particle, electrons, quarks, photons, there's a corresponding field. An electron field, a quark field, a photon field. Think of the photon field, for instance. This field is responsible for the existence of light. It's always there, even in a vacuum, and it's the source of all electromagnetic radiation, from radio waves to X-rays. Now, when we observe light, when we detect a photon, we aren't actually creating a photon from nothing. Instead, we're observing a ripple, a disturbance, an excitation within the photon field. That excitation, that ripple, is what we perceive as a photon. It's like dropping a pebble into the lake, you create waves. Similarly, when energy is added to the photon field, it manifests as a particle we call a photon. Conversely, a photon carrying energy away from an atom, effectively removing an excitation from the field. This process of excitation and de-excitation is incredibly precise. The amount of energy involved, the energy of the excitation, is directly related to the properties of the particle, its mass and its momentum. This is beautifully captured by Einstein's famous equation, E equals mc2, but within the framework of QFT, it's understood as the energy added to or removed from a specific field. The same principle applies to other particles. Electrons aren't tiny balls, they're excitations of the electron field. Quarks, the building blocks of protons and neutrons, also exist as excitations of their own corresponding fields. These fields aren't just theoretical constructs. They have measurable consequences. Scientists can detect these excitations, these particles, and their interactions with each other. A particularly fascinating aspect of QFT is how it handles interactions. When two particles interact, it's not like one particle colliding with another and bouncing off. Instead, they exchange excitations within their respective fields. For example, when two electrons repel each other, they are exchanging photons, excitations within the electromagnetic field. This exchange of excitations is what we experience as the force between the electrons. It's a constant, dynamic dance of energy flowing between the fields. This exchange process governs the way that particles interact, creating the forces we observe in the universe. Furthermore, QFT provides a way to understand things like particle creation and annihilation. It's not a violation of conservation laws, but rather a consequence of the dynamic nature of these fields. A particle can briefly appear when enough energy is added to the field, a temporary excitation. Conversely, when a particle loses enough energy, it can disappear, returning its energy to the field. The mathematics of QFT are incredibly complex, built upon the tools of quantum mechanics and special relativity. But the core idea, that particles are excitations of underlying fields, is remarkably elegant and provides a consistent framework for understanding the most fundamental aspects of the universe. It's a testament to the power of human curiosity and our ability to unravel the deepest mysteries of existence. Ultimately, quantum field theory provides a much richer, more nuanced, and frankly, more exciting picture of reality than the simple idea of particles bouncing around in empty space. It's a story of constant interaction, of energy flowing through the fabric of space and time, a story that continues to be explored and refined by scientists today. It's a story about the universe's deepest secrets, and a reminder that the most profound discoveries often come from challenging our most fundamental assumptions. The universe, as we've begun to understand it, isn't built of solid things like rocks and trees. It's constructed from something far stranger, something that operates according to rules so counterintuitive they can make your head spin. For a long time, physicists were grappling with this strangeness, trying to build a consistent picture of what makes up everything around us. Slowly, painstakingly, they've developed a framework called the Standard Model of Particle Physics. It's not a complete theory. There are still big unanswered questions, but it's remarkably successful at predicting the behavior of the fundamental building blocks of matter and the forces that govern their interactions. At its heart, the Standard Model describes three fundamental types of particles: quarks, leptons, and gauge bosons. These aren't things in the conventional sense. They're excitations, ripples, or vibrations within underlying fields that permeate all of space. Think of it like this. Space isn't empty. It's filled with these invisible fields, and when enough energy is concentrated in a small area, it creates a detectable particle. Let's begin with the quarks. These are the most fundamental particles we know of, and they're the building blocks of protons and neutrons, which in turn make up the nuclei of atoms. There are 6 flavors of quarks, categorized into 3 generations. The first generation includes the up quark and the down quark, which are the most common and are responsible for the vast majority of the mass we observe in the universe. The second generation consists of the charm quark and the strange quark, and the third generation comprises the top quark and the bottom quark. Each quark flavor has a corresponding antiquark, a particle with the same mass but opposite charge. When a quark and antiquark meet, they annihilate each other, releasing energy in the form of photons or other particles. The charges of the quarks are fractional. Up quarks have a positive charge of +2,3, and down quarks have a negative charge of -1,3. These charges, combined in specific arrangements, determine the electrical properties of atoms and molecules. Now let's move on to the leptons. These are another family of fundamental particles, and they're even more elusive than quarks. Like quarks, they also come in 3 generations. The first generation includes the electron, which is the familiar particle orbiting the nucleus of an atom, and its corresponding anti-electron, the positron. The second generation consists of the muon and the tau lepton, along with their antileptons. The third generation includes the heaviest leptons, the tau lepton and the tau anti-elepton. Each of these leptons carries a fundamental electric charge, but unlike quarks, their charges are all whole numbers, -1 for the electron, -1 for the muon, -1 for the tau lepton, and so on. Leptons don't experience the strong nuclear force. They only interact via the weak nuclear force and electromagnetism. Their masses are significantly smaller than those of the quarks, and they play a crucial role in radioactive decay processes. Finally, we have the gauge bosons. These are the force carriers, the particles that mediate the fundamental forces of nature. There are 4 types of gauge bosons, each associated with a different force. The photon is the carrier of the electromagnetic force, responsible for interactions between electrically charged particles. The W and Z bosons carry the weak nuclear force, which is responsible for radioactive decay and certain types of particle interactions. These bosons are massive, unlike the massless photon, and this mass is a key factor in the weakness of the weak force. And then there's the graviton, a theoretical particle that would carry the force of gravity. While the graviton has yet to be directly observed, its existence is predicted by our current understanding of quantum field theory. The Standard Model doesn't just list these particles, it describes how they interact. Particles aren't isolated entities. They constantly exchange gauge bosons, mediating forces between them. For instance, an electron and a proton aren't attracted to each other directly. Instead, they repel each other due to the electromagnetic force, mediated by the exchange of photons. The W and Z bosons also play a role in interactions between quarks, contributing to the strong nuclear force that binds them together within the nucleus. The model elegantly explains a huge range of phenomena, from the stability of atoms to the behavior of subatomic particles in high-energy collisions. However, the standard model isn't without its limitations. It doesn't include gravity, doesn't explain the matter-antimatter asymmetry in the universe, and it relies on parameters that are determined experimentally rather than predicted theoretically. Furthermore, it has a large number of free parameters, hinting that there might be a more fundamental theory waiting to be discovered. The quest to refine and extend the standard model continues, pushing the boundaries of our knowledge about the deepest workings of the cosmos. It's a story still unfolding, a testament to human curiosity and our unwavering desire to understand the universe, one particle at a time. The universe, at its most fundamental level, doesn't like to be left alone. It's a remarkably restless place, governed by probabilities and uncertainties. We've spent the last few parts exploring how particles behave, how they interact, and how they seem to exist in multiple states simultaneously. A state we can describe best as being in a state of flux. Now, let's delve into a particularly strange and fascinating phenomenon, the quantum Zeno effect. It's a concept that beautifully illustrates the profound influence observation has on quantum systems. At its core, the Zeno effect, named after the ancient Greek philosopher Zeno of Elea, describes a counterintuitive behavior. Zeno famously presented a series of paradoxes, most notably the arrow paradox, which challenged the idea of motion by suggesting that an arrow in flight is always, at every instant, at rest. The quantum Zeno effect takes this idea and applies it to the quantum world. Consider a tiny, isolated atom. Let's say this atom has a small probability of transitioning from a lower energy state to a higher energy state, a simple jump. This transition isn't instantaneous. It's governed by the rules of quantum mechanics, where particles can exist in a superposition of states until measured. However, if we repeatedly observe this atom and check to see if it's still in its original state, something remarkable happens. Each time we observe the atom and determine it hasn't changed, we're effectively resetting its quantum state. The very act of observation forces the atom to re-enter the superposition of states, essentially preventing the transition from occurring in the first place. It's as though the measurement process is exerting a stabilizing influence, holding the system back from changing. The more frequently we observe, the stronger this stabilizing effect becomes. It's not simply a matter of delaying the transition, it's actively preventing it. Imagine repeatedly checking on a spinning top. If you constantly watch it and note when it starts to wobble, you'll find it becomes increasingly difficult for it to start wobbling in the first place, as your observation is suppressing the movement. The key here is the idea of collapse, the process by which the wave function describing a quantum system abruptly changes its state upon measurement. Before the observation, the atom exists in a blurry, probabilistic state, a mixture of possibilities. The act of measurement forces it to choose one of those possibilities. It's important to understand that observation isn't necessarily a conscious act. It doesn't require a human being peering at the atom. Any interaction that determines the state of the system, even a collision with another particle, can trigger the collapse of the wave function and initiate the Zeno effect. The crucial factor is that the measurement provides information about the system's state. There have been experiments that have beautifully demonstrated this effect. Researchers have used precisely timed pulses of light to excite atoms, and then, by rapidly repeating measurements, effectively frozen the atoms in their initial state, preventing them from transitioning to a higher energy level. It's akin to a tiny quantum brake being applied. The magnitude of the Zeno effect depends on several factors, including the rate of observation and the strength of the transition itself. Transitions that occur quickly are more susceptible to being frozen. The more frequently the system is checked, the more pronounced the effect. Now, let's consider a slightly more complex scenario. Imagine a system consisting of two atoms interacting with each other. One of the atoms has a probability of decaying, transforming into a different particle over a certain period. If we repeatedly observe this atom and determine that it hasn't decayed, we're not just preventing the decay of a single atom, we're effectively inhibiting the entire interaction, slowing down the decay process of the whole system. The Zeno effect isn't just a theoretical curiosity. It has potential applications in areas like quantum computing and quantum information processing. Controlling and manipulating the Zeno effect could be used to stabilize quantum states, which are notoriously fragile and susceptible to environmental noise. Maintaining coherence, the ability of a quantum system to exist in a superposition, is vital for these technologies, and the Zeno effect offers a potential strategy for achieving this. Furthermore, the Zeno effect highlights a fundamental tension in our understanding of the universe. It suggests that the act of observation isn't just a passive process of recording information. It's an active participant, shaping reality at the most basic level. It forces us to question the very nature of measurement and its role in the quantum world. While the concept can seem counterintuitive, the quantum Zeno effect provides a fascinating window into the strange and wonderful behavior of matter at the quantum scale. It's a reminder that the universe isn't always what it seems, and that the simplest assumptions can lead to the most profound and perplexing discoveries. It's a beautiful demonstration of how observation truly is a force to be reckoned with in the quantum realm. The universe, at its most fundamental level, isn't a place of neat, isolated things. It's a swirling, vibrating, interconnected dance of energy. We've spent some time exploring how this energy manifests as particles, their interactions governed by the elegant rules of quantum field theory. We've also touched upon the idea that simply observing a quantum system can dramatically alter its behavior, a phenomenon known as the quantum Zeno effect. But these are just pieces of a larger, more mysterious puzzle, the gradual disappearance of the peculiar qualities that define the quantum world. This is the story of decoherence. Consider a single electron, initially existing in a state of superposition, meaning it's simultaneously in multiple possible locations, with multiple possible momenta, all at the same time. It's not that we don't know where it is. It truly exists in a blend of all those possibilities. This is a fundamental aspect of quantum mechanics, a reflection of the inherent uncertainty at the core of reality. However, this state, this shimmering existence of multiple potentials, is incredibly fragile. The slightest interaction with its environment can trigger a process that swiftly and almost irreversibly collapses this superposition. It's like trying to hold a handful of sand. The moment you try to gather it, the grains slip through your fingers. The universe, it seems, doesn't like things to remain in this uncertain state. This interaction isn't necessarily a violent collision. It can be something as subtle as a photon of light bouncing off the electron, a vibration from the surrounding air molecules, or even a stray magnetic field. Each of these interactions acts as a tiny, continuous measurement, effectively recording the electron's state. The electron's superposition, that delicate blend of possibilities, begins to blur. Imagine a beautiful, complex melody played on a glass harp. The individual glass rods vibrate, creating a rich and layered sound. But if you introduce even a tiny amount of dust into the air, the vibrations are disrupted. The notes become muffled, the harmony fades, and the music slowly loses its complexity. This disruption is analogous to what happens during decoherence. The key element in decoherence is the concept of phase, the characteristic wave-like behavior of quantum systems. Quantum waves aren't just shapes. They're defined by their phase, representing the timing and amplitude of the wave. When a quantum system interacts with its environment, it exchanges energy and information, essentially correlating its phase with the phase of the environment. This correlation, this spreading of phase, is what destroys the superposition. Let's use a slightly different analogy. Think of a perfectly balanced spinning top. It remains stable for a long time, executing a smooth, consistent rotation. But if you lightly touch it, even a fleeting brush of air, it begins to wobble and eventually falls over. That wobble represents the loss of the initial, stable state. The environment, in this case the air, has imparted energy, disrupting the delicate balance. The more complex the quantum system, the faster and more effectively decoherence occurs. A single electron is relatively robust, but a collection of atoms, or even a larger molecule, will decohere incredibly quickly. This is because there are vastly more potential interactions with the environment. Each interaction contributes to the spreading of phase, accelerating the collapse of the superposition. Scientists have devised sophisticated experiments to demonstrate decoherence. One particularly elegant experiment involved using trapped ions, individual atoms suspended in a vacuum and manipulated by electromagnetic fields. Researchers were able to observe the superposition of these ions, but when they attempted to measure their quantum state, the superposition vanished almost instantaneously. This rapid loss of quantum coherence was a direct result of the ions' constant interaction with the electromagnetic fields and the vibrations of the surrounding environment. The interesting part is that decoherence isn't simply a process of destruction. It's not like a sudden, violent shattering of the quantum state. Instead, it's a gradual, continuous process of information exchange between the quantum system and its surroundings. The system loses its ability to maintain its superposition, because it's constantly being influenced by the environment. Decoherence has profound implications for our understanding of quantum computing. Quantum computers rely on the principle of superposition to perform computations far beyond the capabilities of classical computers. However, maintaining the delicate superposition of qubits, the quantum equivalent of bits, is incredibly challenging because of decoherence. Any interaction with the environment can disrupt the superposition and lead to errors in the computation. Therefore, researchers are actively exploring ways to shield qubits from environmental noise and slow down the process of decoherence. Ultimately, decoherence highlights the fundamental tension between the quantum world and the classical world. The quantum world thrives on uncertainty and superposition, but as soon as we attempt to observe or measure a quantum system, we force it to choose a single state, bringing it into alignment with the familiar, predictable rules of our everyday experience. It's a reminder that the universe, at its most fundamental level, is a constant exchange, a never-ending dance of interaction and information. The universe, as we've explored, isn't quite the neat, predictable clockwork we often perceive. At the deepest levels, reality behaves in ways that seem, frankly, quite strange. It's a realm where particles can be in multiple places at once, and where the act of observing can fundamentally alter what's happening. This unusual behavior is the bedrock upon which a revolutionary new technology, quantum computing, is being built. Instead of relying on the bits of conventional computers that represent information as a simple 0 or 1, quantum computers use something far more intriguing: qubits. A qubit isn't just a simpler version of a bit. It's a quantum system, typically based on the properties of atoms, ions, or superconducting circuits. But the key difference lies in its ability to exist in a state of superposition. Think of a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a state that's a combination of both possibilities. A qubit, similarly, can represent 0, 1, and a combination of both simultaneously. It's not that it's switching rapidly between the two states. It genuinely occupies both states at the same time. This is what allows quantum computers to perform calculations in ways that are impossible for even the most powerful classical computers. The underlying physics behind this is rooted in the principles of quantum mechanics. Quantum systems possess measurable properties like energy levels, and these levels aren't neatly defined like the steps on a staircase. Instead, they can exist as a continuous range of possibilities. This blurring of states allows for superposition. A system might exist in a superposition of two energy levels, meaning it has a probability of being in either level when measured. The exact proportions of each possibility are described by mathematical formulas, and these probabilities are constantly shifting until a measurement is made. Let's consider a simplified example: an ion trapped within an electromagnetic field. This ion can exist in two energy states, which we'll call up and down. In superposition, the ion isn't definitively up or down. It's in a state where there's a certain probability of it being up and a corresponding probability of it being down. The ion state is described by a mathematical wave function that represents all the potential states and their associated probabilities. The beauty of this approach is that the computer doesn't need to process information sequentially, one step at a time. Instead, it can explore all possible solutions simultaneously. Now, let's delve into how this superposition is harnessed for computation. Imagine a maze with many possible paths. A classical computer would try each path one by one until it finds the solution. A quantum computer, thanks to superposition, can effectively explore all paths simultaneously. It's like sending out a multitude of copies of itself, each exploring a different route. The computer then uses quantum interference, another fascinating quantum effect, to amplify the probability of the correct answer and diminish the probability of incorrect answers. Quantum interference is, in essence, the interaction of these wave-like probability distributions. When two waves overlap, they can either add together, constructive interference, or cancel each other out, destructive interference. In the context of quantum computing, the wave functions representing different solutions to a problem interact, and the interference patterns dictate which solutions become more likely. The more frequently a particular solution appears in the interference pattern, the higher the probability of obtaining that solution when the qubit is measured. The act of measuring a qubit, however, is critical. When a qubit is measured, its superposition collapses. The wave function instantly transitions from representing all possibilities to settling into one definite state, either 0 or 1. This collapse is irreversible. Therefore, quantum algorithms are carefully designed to maximize the probability of obtaining the desired result before a measurement is made. It's like steering those copies of ourselves through the maze, subtly influencing their paths to converge on the exit. The challenge in building quantum computers lies in maintaining this delicate superposition state. Superposition is incredibly fragile. Any interaction with the environment, even the smallest vibration or fluctuation in temperature, can cause decoherence. Decoherence is the process by which a qubit loses its quantum properties and collapses into a definite state. Maintaining coherence, and therefore the ability to perform computations, requires extremely precise control and isolation of the qubits. Scientists are exploring various methods to mitigate decoherence, including operating at temperatures close to absolute zero and employing error correction techniques. Despite these challenges, the potential impact of quantum computing is enormous. Certain types of calculations, like factoring large numbers or simulating complex molecules, are exponentially more difficult for classical computers. Quantum computers, leveraging superposition and interference, could potentially solve these problems within a reasonable time frame. This could revolutionize fields such as drug discovery, materials science, and artificial intelligence. The journey to fully realize the potential of quantum computing is ongoing, but the underlying principles, superposition and interference, represent a fundamentally new way of processing information, hinting at a future where the bizarre and wonderful properties of the quantum world unlock solutions to some of humanity's greatest challenges. The universe, as we've been exploring, isn't governed by simple rules feels like a perfectly predictable game of chess. At its most fundamental level, reality dances to a tune of probability, a tune we call quantum mechanics. This inherent fuzziness presents incredible opportunities, and one of the most exciting applications of quantum mechanics is something called quantum cryptography. It's a way to send messages with a level of security that's fundamentally impossible to achieve with traditional methods. Traditional cryptography relies on mathematical algorithms that are incredibly complex, but ultimately, they are still based on the possibility of someone breaking the code. Clever algorithms can be developed, but if a sufficiently powerful computer eventually finds a way to crack the algorithm, the security is gone. This is like using a complicated lock with a key. Eventually, someone might figure out how the lock works. Quantum cryptography takes a dramatically different approach. Instead of relying on complex algorithms, it uses the very properties of quantum mechanics, specifically the behavior of photons, to ensure that any attempt to eavesdrop on a message instantly reveals itself. Let's consider a system where we want to send a secret key to our friend Alice. We use a device, let's call it a quantum key distribution, QKD system, to do this. This system involves two special photons, often referred to as entangled photons. Entanglement is a truly bizarre quantum phenomenon. When two photons become entangled, they become linked in a profound way. Even if we separate them by vast distances, across a city, across a country, or even across the galaxy, their properties remain correlated. Measuring the state of one photon instantaneously influences the state of the other, a connection that seems to defy our everyday understanding of space and time. In our QKD system, Alice holds one of the entangled photons and Bob holds the other. Both Alice and Bob measure their photons using detectors. The key is that they're not simply measuring a fixed property like polarization, which we've discussed in previous parts. Instead, they're making a random measurement, choosing between different possible outcomes. Let's say horizontal or vertical for polarization. These measurements are truly random, governed by the unpredictable nature of quantum mechanics. Crucially, Alice and Bob don't immediately send the results of their measurements back to each other. Instead, they each keep a record of their measurements. After a predetermined period, they compare a subset of their measurement results over a public, but authenticated, channel. This comparison reveals whether their photons were truly entangled. Did their measurements correlate as they should? Here's the magic. If anyone, let's call him Eve, tries to intercept and measure the photons during their journey, her attempt inevitably disturbs the quantum state. Quantum mechanics dictates that the act of measurement fundamentally changes the system. Eve's intervention, no matter how subtle, introduces errors into the correlation between Alice's and Bob's measurements. Because the correlations are based on the delicate quantum state, any attempt to eavesdrop leaves a detectable trace. Alice and Bob can analyze the error rate, the number of errors in their correlated measurements, and if it's above a certain threshold, they know that someone has been trying to listen in. They immediately discard the key and start the process again. The beauty of this system isn't just that it's secure, it's that it's provably secure, based on the fundamental laws of physics. It's not vulnerable to clever algorithms or computational power. It relies on the unavoidable disturbance caused by any attempt to observe the quantum system. This is unlike traditional encryption, where security relies on the assumption that a potential attacker won't eventually develop the tools to break the code. There are different variations of QKD protocols, each with its own strengths and weaknesses. Some systems use single photons, while others employ polarization-entangled photons. The technology is still relatively young, and significant challenges remain in terms of distance and cost. Sending entangled photons over long distances is complicated by signal loss and decoherence, the breakdown of the quantum state due to interactions with the environment. However, researchers are actively developing methods to overcome these hurdles, including quantum repeaters that can extend the range of QKD systems. Furthermore, scientists are exploring ways to integrate QKD into existing communication networks, creating a layered approach to security. This could involve using QKD for the most sensitive data transmission and combining it with traditional encryption for less critical communications. The potential implications of quantum cryptography are enormous. It's not just about securing financial transactions or government secrets. It's about safeguarding the very fabric of our digital world. As our reliance on communication grows, the need for truly secure channels becomes increasingly urgent. Quantum cryptography offers a path towards that security, a security rooted in the most fundamental laws of the universe. The journey to fully realize the potential of quantum cryptography is ongoing. But with each advance in quantum technology, we move closer to a future where communication is truly unbreakable, a future guided by the strange and wonderful world of quantum mechanics. The very fabric of our understanding of the universe has been undergoing a profound shift, driven by the seemingly bizarre rules governing the subatomic world. What began with the observations of individual particles, their wave-like behavior, their ability to be in multiple places at once, has begun to suggest that the universe itself might not be the neatly ordered, deterministic place we once assumed. Quantum cosmology is the burgeoning field attempting to apply these quantum principles not just to tiny particles, but to the entirety of existence, the cosmos itself. It's a truly audacious undertaking, venturing into the realms of space, time, and gravity, all of which are fundamentally interwoven. For centuries, cosmology operated under the assumption of a space-time continuum, a stage upon which the drama of the universe unfolded according to fixed laws. General relativity, Einstein's masterpiece, brilliantly described this stage, explaining gravity as the curvature of space-time caused by mass and energy. However, this model struggled to reconcile with quantum mechanics, particularly at the very beginning, just moments after the Big Bang. The conditions were so extreme, infinite density, unimaginable energy, that the rules we understand simply ceased to apply. It was like trying to use a hammer to build a skyscraper. The tools were fundamentally incompatible with the scale of the task. The earliest moments of the universe, often referred to as the Planck epoch, are shrouded in mystery. Our current physics breaks down the conventional understanding of space and time as distinct entities, a three-dimensional stage and a linear timeline, simply doesn't fit. Quantum cosmology proposes a radically different picture, one where space and time themselves are quantized, meaning they are not continuous but exist in discrete, fundamental units. Think of it like a digital image. It appears smooth to our eyes, but it's actually made up of tiny pixels. Similarly, spacetime might be composed of incredibly small chunks or grains, a concept known as spacetime foam. One influential model, the Hartle-Hawking state, attempts to describe the universe's earliest state as a smooth, featureless void, governed by the laws of quantum mechanics. This isn't a vacuum in the traditional sense. It's a state of maximum uncertainty where all possibilities exist simultaneously. It's a purely mathematical description, lacking any specific geometrical properties. The universe in this early stage isn't shaped or defined. It's simply the potential for everything to be. Another significant approach, championed by Roger Penrose, incorporates ideas from general relativity and quantum mechanics by suggesting that the Big Bang wasn't a single point of explosion, but rather a quantum bounce. This concept proposes that the universe didn't originate from a singularity, but rather emerged from a previous contracting universe. The contraction continues endlessly, with each cycle ending in a bounce. This cyclic model attempts to resolve the singularity problem and offers a way to avoid the need for an initial beginning. The universe, in this view, is eternally oscillating between expansion and contraction, though the details of this process are still intensely debated. The implications of a quantum universe extend far beyond just the very beginning. Quantum fluctuations, tiny, random variations in energy, are believed to have played a crucial role in seeding the formation of galaxies and large-scale structures. These fluctuations, amplified by inflation, a period of extremely rapid expansion in the very early universe, eventually grew into the gravitational wells that attracted matter, leading to the formation of stars and galaxies. It's a beautiful illustration of how the smallest quantum events could, over vast stretches of time, sculpt the largest structures in the observable universe. Furthermore, quantum entanglement, the perplexing phenomenon where two particles become linked in such a way that they share the same fate, no matter how far apart they are, is also being considered in the context of cosmology. Some scientists theorize that entanglement might have played a role in the homogeneity of the universe. Why the cosmic microwave background radiation, the afterglow of the Big Bang, is so remarkably uniform across the sky. It's a challenging idea, and the mechanisms are still largely speculative. But the connection between quantum correlations and the large-scale structure of the universe is an active area of research. The measurement problem in quantum mechanics, the question of how a definite state arises from a superposition of possibilities, also has profound implications for cosmology. If the universe is fundamentally quantum, then the act of observation, the very process of measurement, might have played a role in shaping the universe. This isn't necessarily a conscious observer, but rather any interaction with the quantum system. The universe, in this view, is constantly evolving through interactions, and the observer is not merely a passive witness, but an active participant. It's a disconcerting thought, pushing the boundaries of our intuition about reality. Despite the significant challenges and open questions, quantum cosmology offers a potentially revolutionary way of understanding our place in the universe. It suggests that the cosmos is not a static, predetermined stage, but a dynamic, evolving system, governed by the probabilistic rules of quantum mechanics. It invites us to reconsider our most basic assumptions about space, time, and existence. As our understanding of quantum mechanics deepens, and as new experimental data emerges, we may one day gain a truly profound understanding of the origin, evolution, and ultimate fate of the universe. A journey fueled by the strange and wonderful rules that govern the smallest scales of reality. The unsettling thing about quantum mechanics is that it doesn't like to be pinned down. It's a world where things aren't certain until they're observed, a world of probabilities shimmering in every possible state. We've seen how a particle, like an electron, can exist in multiple places at once, a blurry dance of potential. But what happens when we try to understand what's really going on, when we attempt to fully define its position, its momentum, its very existence? That's where the many worlds interpretation, or MWI, enters the picture, offering a rather startling solution. It began with Hugh Everett III, a brilliant young physicist at MIT in the 1950s. He was deeply troubled by the collapse of the wave function, the sudden, inexplicable transition from a particle existing in multiple possibilities to settling into a single, definite state when a measurement is made. The standard Copenhagen interpretation, the one most physicists subscribed to at the time, suggested this collapse was a fundamental, unexplained process. Everett couldn't accept it. He reasoned that the wave function never actually collapses. Instead, every possible outcome of a quantum measurement simply manifests in its own separate universe. Let's consider a classic thought experiment, Schrödinger's cat. The cat, inside a sealed box with a radioactive atom, a detector, and a vial of poison, is in a superposition of being both alive and dead until the box is opened and observed. In the Copenhagen interpretation, the act of opening the box forces the wave function to collapse, and the cat becomes definitively either alive or dead. But Everett's interpretation says something completely different. When the atom decays or doesn't decay, the probability is equally important. The universe splits. In one universe, the atom decays, the detector clicks, the poison is released, and the cat dies. In another, identical universe, the atom doesn't decay, the detector remains silent, and the cat lives. It's crucial to understand that these are just other universes existing far away, inaccessible to us. They are branches of our own universe, born from every quantum event. Every time a quantum particle makes a choice, every time an electron passes through one slit or the other in the double-slit experiment, for example, a new universe is created. It's not that we are perceiving different realities. Rather, our existence is continually split into countless versions, each experiencing a different outcome. The implications are profound and, frankly, a little difficult to grasp. Every decision you've ever made, every random event that's ever occurred, has created a new universe where the opposite occurred. If you chose to have tea this morning, there's a universe where you had coffee. If a coin landed heads, there's a universe where it landed tails. The sheer number of these universes is staggering, constantly multiplying with every quantum event. Some estimates suggest there are far more universes than there are atoms in our observable universe, a truly mind-boggling scale. Now, the beauty and the challenge of the MWI is that it elegantly avoids the problem of wave function collapse. It's a deterministic theory. The wave function always evolves according to the Schrödinger equation, a deterministic equation. There's no randomness, no collapse. Instead, what appears to be randomness to us is simply a consequence of our limited perspective. We only experience one branch of the multiverse. We are, in a sense, just observers within a vast, branching tree of realities. It's important to note that the MWI doesn't provide a way to travel between these universes. The separation is fundamental, rooted in the quantum realm. It's not like stepping through a doorway. It's a splitting of existence. The universes are independent and unobservable by each other. Furthermore, while the MWI neatly solves the problem of wave function collapse, it introduces its own set of questions. It raises the question of why we find ourselves in this particular branch of the multiverse, and why we perceive reality as we do. What criteria determine which universe we inhabit? These questions remain largely unanswered, adding to the intrigue and complexity of the theory. Despite these unanswered questions, the many worlds interpretation remains a serious contender in the ongoing debate about the interpretation of quantum mechanics. It offers a compelling, mathematically elegant, and profoundly unsettling vision of reality. A reality where the universe is not just a single, solitary entity, but an infinite, ever-branching tapestry of possibilities. It's a reminder that perhaps the most fundamental secrets of the universe are the most difficult to comprehend, and that our understanding of reality may be far more strange and wondrous than we ever imagined. The continued exploration of quantum mechanics keeps revealing new layers of complexity, and the many worlds interpretation, with its implications for our place in the cosmos, continues to spark debate and inspire awe. As we delve deeper into the quantum realm, we may come to realize that the universe is not what it seems, and that the very act of observation shapes the reality we experience. Sweet dreams, and perhaps, in the quietest moments, consider the infinite possibilities that lie within your own existence. The universe, as we've begun to understand it, doesn't always play by the rules we're used to. Our everyday experience is built on a foundation of cause and effect. If you push a ball, it rolls. If you heat a pan, it gets hot. But at the tiniest scales, the world behaves in a profoundly stranger way, governed by the principles of quantum mechanics. Before we ventured into the concepts of entanglement, it was already clear that the behavior of subatomic particles was fundamentally probabilistic, existing in a haze of possibilities until observed. However, the question remained: Were these seemingly random behaviors truly independent, or was there something more interconnected at play? This is where John Stuart Bell's theorem stepped into the picture, offering a revolutionary way to investigate this crucial question. Bell's theorem, formulated in 1964, wasn't about proving that quantum mechanics was right or wrong. Instead, it provided a mathematical framework to test whether nature adhered to what we call local realism. Local realism consists of two key assumptions. The first, locality, states that an object can only be influenced by its immediate surroundings. Information, or influence, cannot travel faster than the speed of light. This seems intuitively obvious. A distant object can't instantly affect something nearby, right? The second part of the assumption is realism, which proposes that physical properties of an object, like its polarization, for example, are definite and predetermined, even when we aren't measuring them. It's like a coin spinning in the air. It's either heads or tails even before it lands. Realism suggests that the polarization of a photon, for instance, has a definite direction before we measure it. Bell's genius was to derive an inequality, now known as Bell's inequality, that would provide a quantitative test for these assumptions. This inequality set a limit on the statistical correlations that could be observed between measurements made on two entangled particles. Let's consider two entangled photons. These photons are created in a way that ensures their properties, like polarization, are correlated. This correlation isn't about knowing one property beforehand. It's about a fundamental connection established during their creation. Now, imagine we send these photons to two distant observers, Alice and Bob, who can each measure the polarization of their photon along different axes. The Bell's inequality states that no matter how cleverly Alice and Bob choose their measurement axes, the statistical correlations between their results will always fall below a certain limit. The surprising thing began to emerge with experimental verification. In the 1970s and 80s, physicists like Elaine Aspect and his team conducted a series of groundbreaking experiments. They used crystals to generate pairs of entangled photons, and then sent these photons to separate locations, carefully shielding the apparatus from any local influences, like vibrations or electromagnetic fields that might subtly bias the measurements. The key was to demonstrate that the correlations observed between Alice and Bob's measurements consistently violated Bell's inequality. This meant that the universe wasn't obeying local realism. The statistical correlations were significantly stronger than what Bell's inequality predicted. The implications were profound. The experiments demonstrated that the properties of entangled particles are not determined locally. The act of measuring one particle instantaneously influences the state of the other, regardless of the distance separating them. It's as if the two photons are connected by an invisible thread, allowing them to know about each other's state instantaneously. This isn't about sending signals faster than light. It's about a deeper, more fundamental connection within the quantum realm. Think of it not as a messenger, but as a shared state. Crucially, Bell's theorem and these experiments didn't violate Einstein's theory of special relativity, which states that nothing can travel faster than light. The influence between the entangled particles isn't a physical transmission of information. Instead, it's a change in the shared quantum state itself. It's a change that happens instantaneously. But this change doesn't allow us to send messages. If Alice tries to send a message to Bob by manipulating her photon, Bob won't receive the message because the outcome of his measurement remains random. The interpretation of these findings remains a topic of ongoing debate among physicists. Some believe that it suggests a deeper level of reality, where space and time may not have the same meaning we perceive them to have. Others see it as evidence for the inherent non-locality of quantum mechanics, a fundamental property of the universe. The experiments powerfully demonstrate that the universe is inherently interconnected in ways we are still struggling to fully understand. The verification of Bell's theorem and the subsequent experiments are considered one of the most significant achievements in 20th century physics. They forced a radical rethinking of our concepts of space, time, and causality. The seemingly bizarre behavior of entangled particles has not only deepened our understanding of the quantum world, but also opened up possibilities for revolutionary technologies, such as quantum computing and quantum cryptography, which rely on this fundamental interconnectedness. The universe, it seems, is far stranger and more wonderful than we ever imagined. And while the full implications of non-locality are still being explored, one thing is certain. The quest to understand the quantum realm continues to push the boundaries of human knowledge. The universe, at its most fundamental level, doesn't seem to enjoy being observed. It's a wonderfully strange notion and the heart of a persistent puzzle in quantum physics, the measurement problem. Before we delve into the specifics, let's consider what we mean by quantum. We've discussed how particles, like electrons, don't possess definite properties, a position, momentum, spin, until they are measured. Instead, they exist in a state described by a wave function, a mathematical representation of all the possibilities a particle could have. This wave function isn't a physical thing. It's a probability distribution, telling us the likelihood of finding the particle in a particular state if we were to look. It's like a blurry cloud of potential, encompassing all possibilities simultaneously. This blurry state is incredibly potent. It suggests that the universe is fundamentally indeterminate until acted upon. The key question then arises: what triggers this transition from a hazy potential to a definite reality? What causes the wave function to collapse into a single, observable outcome? This is where the role of the observer, and more accurately the act of measurement, becomes profoundly mysterious. It's not simply that we are looking. The process of measurement itself seems to be the catalyst. Let's illustrate with a classic experiment, the double-slit experiment. Particles, like photons, are fired at a barrier with two slits. Without observation, they pass through both slits simultaneously, creating an interference pattern on a screen behind the barrier, a characteristic signature of wave behavior. It's as if the photon is exploring both paths at once. However, the moment we try to observe which slit the photon passes through, the interference pattern vanishes. Instead, we see two distinct bands, as if the photon has chosen one slit or the other. This isn't just a technical glitch. The very act of determining the photon's path fundamentally alters its behavior. Before measurement, it existed in this superposition of states, both passing through both slits. The act of measurement, even a simple detection, forces it to choose one path, destroying the interference pattern. This raises some extremely unsettling questions about the nature of reality. Several interpretations attempt to address this problem, each offering a different perspective. The Copenhagen interpretation, largely championed by Niels Bohr, posits that the wave function doesn't truly collapse, but rather that the measurement forces us, the observers, to interact with the system, and this interaction is what brings about the definite outcome. It's a deeply contextual view, suggesting that reality is fundamentally shaped by our observations. Another prominent idea is the many worlds interpretation. As we've touched upon, this interpretation avoids wave function collapse entirely. Instead, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. In one branch, the photon passes through the left slit. In another, it passes through the right. We only experience one branch, but all possibilities continue to exist in parallel universes. The measurement doesn't change the system. It simply causes a split in reality. However, these interpretations are far from universally accepted. They raise incredibly complex philosophical questions about consciousness, objectivity, and the very definition of reality. Another approach, known as objective collapse theories, suggests that wave function collapse is a real physical process, independent of any observer. These theories propose mechanisms, perhaps involving vacuum fluctuations or decoherence, that could trigger spontaneous collapse. A significant element within these debates is decoherence. Decoherence describes the process by which a quantum system loses its coherence, its ability to maintain a superposition of states due to interactions with its environment. The environment, consisting of countless particles, effectively measures the system, even without a conscious observer. This interaction rapidly destroys the delicate superposition, leading to the appearance of classical behavior. It's a subtle but profoundly important concept. It's tempting to think of the observer as some kind of magical agent, but that's not the case. The crucial factor isn't consciousness itself, although that remains a fascinating area of inquiry. It's the interaction, the transfer of information between the measuring device and the quantum system. This interaction fundamentally alters the system's state, forcing it to adopt a definite value. The measurement problem highlights the limitations of our everyday intuitions when applied to the quantum world. Our brains evolved to navigate a world where objects have definite properties, but at the quantum scale, this isn't necessarily true. The universe operates according to different rules, and these rules are most profoundly revealed when we attempt to observe them. Ultimately, the measurement problem remains one of the most challenging and debated topics in modern physics. While we've gained valuable insights into the underlying processes, a complete and universally accepted solution remains elusive. It serves as a powerful reminder that our understanding of the universe is constantly evolving, and that the most fundamental aspects of reality may forever defy our intuitive grasp. It's a problem that keeps physicists and philosophers occupied, prompting continued research and stimulating contemplation about the nature of existence itself. The world, as we usually understand it, is built on big, solid things: a rock, a tree, a human being. We experience gravity, friction, and predictable forces. But peering into the incredibly tiny realm of biology reveals something wonderfully surprising. Quantum mechanics isn't just a quirk of the universe at large. It's actively shaping life itself. This burgeoning field, called quantum biology, explores how the bizarre laws governing particles like electrons and photons influence the fundamental processes within living organisms. It's a reminder that the universe is far stranger and more intricately connected than we might initially suppose. One of the most compelling areas of research lies in the realm of photosynthesis. For decades, scientists believed that plants efficiently converted sunlight into energy through a series of well-defined chemical reactions. However, recent studies have begun to suggest that quantum effects play a crucial, and perhaps even dominant, role in this remarkably fast and efficient process. Consider the journey of a photon of light as it enters a leaf. When the sunlight hits a chlorophyll molecule, the green pigment responsible for capturing light energy, the photon doesn't simply deposit its energy and move on. Instead, quantum mechanics dictates that the photon can exist in a state of superposition, meaning it briefly exists in multiple states simultaneously. It's like a ghostly echo of the photon, exploring all possible paths within the chlorophyll molecule before settling down. This isn't a casual fluctuation. The mathematics shows that the photon is genuinely in multiple locations at once, influenced by quantum tunneling. Tunneling is a peculiar phenomenon where a particle can pass through a barrier, even if it doesn't have enough energy to overcome it classically. In the context of photosynthesis, this allows the photon to explore all possible energy transfer pathways within the chlorophyll molecule, drastically increasing the chances of finding the optimal route to excite an electron. It's like a tiny explorer tirelessly trying every corridor in a vast building until it finds the one leading to the destination. The electron, once excited by the photon, then begins its journey along an exciton pathway. This isn't a simple, linear path. Quantum simulations have shown that the electron doesn't travel in a straight line. Instead, it's influenced by quantum fluctuations and quantum coherence, maintaining the wave-like properties of the electron for a brief period. This coherence allows the electron to explore multiple pathways simultaneously, effectively creating a quantum superhighway within the photosynthetic complex. Scientists use sophisticated computer simulations, often drawing on the principles of quantum computing, to model these incredibly complex interactions. These simulations aren't just educated guesses. They're built upon the fundamental equations of quantum mechanics. The accuracy of these simulations relies on accurately representing the quantum behavior of electrons and photons within the biological system. Furthermore, research suggests that quantum entanglement might even be involved. Entanglement, famously demonstrated by Einstein, describes a situation where two or more particles become linked in such a way that they share the same fate, no matter how far apart they are. While the exact role of entanglement in photosynthesis is still under investigation, some theories propose that entangled electron pairs could be involved in rapidly transferring energy across the photosynthetic complex, further enhancing the efficiency of the process. It's a concept that sounds like something from science fiction, but the underlying physics is undeniably real. Beyond photosynthesis, quantum biology is also being explored in other areas of biology. For instance, enzymes, the catalysts that speed up biochemical reactions, are believed to rely on quantum tunneling to facilitate the movement of atoms and molecules during their catalytic cycles. The precise mechanisms remain challenging to unravel, as observing quantum effects in a warm, wet, and noisy biological environment is incredibly difficult. However, researchers are developing innovative experimental techniques, like using ultra-cold temperatures and specialized spectroscopic methods, to probe these quantum phenomena. Another fascinating area of investigation concerns avian navigation. Birds, particularly migratory species, possess an extraordinary ability to sense the Earth's magnetic field and navigate vast distances. Recent research indicates that this navigation process might involve quantum entanglement between electrons in the bird's eye, allowing them to detect incredibly faint magnetic fields. This theory proposes that the bird's retina acts as a quantum compass, using the sensitive vibrations of electrons to perceive the direction of magnetic north. The implications of quantum biology are profound. It fundamentally alters our understanding of life, suggesting that biological processes aren't solely governed by classical physics. Instead, they are deeply intertwined with the bizarre and counterintuitive rules of the quantum world. It pushes the boundaries of scientific knowledge and opens up entirely new avenues for technological innovation, perhaps even leading to the development of bio-inspired quantum computers. As we continue to explore the quantum realm within living organisms, we gain a deeper appreciation for the elegance and complexity of nature. It's a reminder that the universe is not just a collection of separate objects, but a profoundly interconnected system where the smallest particles play a crucial role in shaping the grandest of phenomena, the very existence and function of life itself. And while we may not fully grasp all of its secrets yet, the journey of discovery is itself a beautiful and profound adventure. The universe, as we understand it through Einstein's theory of general relativity, is a grand, elegant dance of space and time, warped and curved by the presence of massive objects. Gravity in this picture isn't a force in the traditional sense, but rather a consequence of how these massive objects shape the very fabric of space-time. It's a beautiful, smooth, and predictable description, consistently accurate at large scales, describing the orbits of planets, the expansion of the universe, and the behavior of black holes with remarkable precision. However, when we try to shrink down to the incredibly small, the realm of quantum mechanics, things get complicated. Quantum mechanics describes the universe at the level of atoms and subatomic particles, and it's characterized by uncertainty, probabilities, and the strange behavior of particles that seem to exist in multiple places at once. The problem arises when we try to reconcile these two incredibly successful, yet fundamentally different, descriptions of the universe. General relativity deals with gravity as a continuous, smooth, geometric property, while quantum mechanics describes the world as discrete, probabilistic, and governed by wave functions. To truly understand the universe, we need a theory that can explain what happens when these two realms overlap, specifically, at the very beginning of the universe, during the Big Bang, or within the singularity of a black hole. These are the extreme environments where both quantum effects and gravitational effects are dominant, and our current theories simply fall apart. Several theories have emerged over the decades attempting to bridge this gap, each with its own unique challenges and proposed solutions. String theory, perhaps the most discussed, suggests that the fundamental building blocks of the universe aren't point-like particles, but rather tiny, vibrating strings. These strings, incredibly small, far smaller than even an atom, exist in 10 or 11 dimensions. We only perceive 3 spatial dimensions and 1 time dimension. Different vibrational modes of these strings correspond to different particles: an electron, a photon, a quark, everything. The idea is that gravity, described by the curvature of spacetime, arises naturally from the motion of these strings. String theory elegantly incorporates gravity into a quantum mechanical framework, but it requires extra spatial dimensions, which haven't been directly observed, and it's notoriously difficult to test experimentally. Another prominent approach is loop quantum gravity. This theory takes a completely different tack, suggesting that space and time themselves are not continuous, but are instead quantized. That is, they are composed of discrete chunks or grains of spacetime. Imagine spacetime not as a smooth sheet, but as a collection of incredibly tiny, interconnected loops. These loops, constantly interacting and exchanging information, form the fundamental building blocks of spacetime. Loop quantum gravity predicts that space and time are not smooth, but have a granular structure at the Planck scale, an incredibly tiny length scale approximately 1.6 x 10^35 meters, far smaller than anything we can currently probe. This quantization of spacetime could potentially resolve the singularity problem at the heart of a black hole, removing the infinitely dense point predicted by general relativity. Then there are other approaches, like asymptotic safety gravity, which posits that gravity might become safe at extremely high energies, avoiding the singularities predicted by standard general relativity. Another idea, spin foam, proposes that spacetime isn't smooth, but is instead filled with a constantly fluctuating foam of connected loops. These theories are complex and mathematically demanding, and the experimental verification of any of them remains a monumental challenge. The Planck scale, the scale at which quantum gravity effects are expected to become significant, is incredibly difficult to access. We can't build a machine to directly probe these tiny distances. However, scientists are exploring indirect methods. One possibility is to look for subtle deviations from general relativity's predictions in strong gravitational fields, such as those near black holes. Another approach involves searching for tiny fluctuations in space-time, which might be a signature of the quantum nature of gravity. Researchers are also studying the cosmic microwave background, the afterglow of the Big Bang, looking for imprints of quantum gravity effects from that early epoch. The quest for a theory of quantum gravity isn't just about understanding the universe's origins or the behavior of black holes. It's fundamentally about our understanding of the nature of space and time themselves. It challenges our most basic assumptions about reality, forcing us to consider whether space and time are truly continuous or whether they are ultimately quantized and discrete. The journey to unify these two pillars of modern physics is ongoing, a testament to the enduring human desire to understand the deepest mysteries of the cosmos. It's a beautiful, frustrating, and incredibly important endeavor, one that may ultimately reshape our understanding of everything. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the strange, beautiful world of quantum physics, a realm of probabilities and interconnectedness. Let your thoughts now drift, calm and unhurried like waves on a still ocean. Allow your awareness to settle, inviting sleep to find you gently.